Hello, in this video I'm going to be talking about the generator. Now remember, in the motor, what we provide is the EMF and the motor provides us with the motion. It's the opposite in the generator. We provide the motion. In return, the generator provides us electricity. This diagram here shows the design of a very simple generator. So the magnets here provide a uniform magnetic field. What do we do with this coil? We rotate it, yeah? Somehow somebody got to do the work to rotate this thing. Can you figure out the direction of the induced currents in this coil? Well, at this instant in time, this wire segment PQ is moving upward, right? So using Fleming's right hand rule, pointing the thumb up because the wire is moving up, you can figure out that the current is going into the screen. So this way. It's the opposite on the other side. The thumb is pointing down because this segment is moving downward at this instant. So the current is coming out of the screen. As you rotate this thing, this coil will behave like a battery with the positive terminal here and negative terminal here. So at this instant, S is the positive terminal because, remember, as a battery, the battery will push currents out of the positive terminal. Of course, half a revolution later, P will become the positive terminal. Another half a revolution later, S will become the positive terminal again. So what we have here is a AC generator because it generates an alternating EMF. So for the direction of the currents, I think of them as wire segments. But if somebody asks me to calculate the magnitude of the induced EMF, I would rather analyze it as a coil because the math will be much easier. Let me show you. So the magnetic field is going rightward. This is when the coil is parallel to the magnetic field. At this orientation, the magnetic flux linkage of the coil is zero because no flux passes through this rectangular area. If you rotate this coil 90 degrees like this, that's when we get the maximum magnetic flux. And the maximum magnetic flux is NBA. N is the number of turns in this coil. A is this rectangular area. So what about when the coil is like this, making an angle of theta with the magnetic field? So when theta is 0, phi is 0, right? And when theta is 90 degrees, phi is NBA. So the expression for the magnetic flux linkage must be NBA sine theta. So this is the guess and check method, yeah? But I expect you to be able to see that the effective area of the coil facing the magnetic field is actually A sine theta. Now, if the coil is being rotated at a constant angular speed, then we can write theta as omega t. Omega is the angular velocity of the rotating coil. Okay, now let me ask you a question. When is the induced EMF at its largest value? Is it when phi is 0 or is it when phi is maximum? Pause the video to think of the answer. If not, I'm going to review the answer now. Now, if you don't think carefully, you might think that the maximum induced EMF happens when the maximum flux linkage is maximum. But you have to remember that Faraday's law says that the induced EMF is proportional to the rate of change of magnetic flux linkage. We can even do the math, just plug in the value for flux linkage, do the differentiation. We can pull out NBA because NBA is a constant. So end up we have to differentiate sine omega t, which will give us cosine omega t with a omega outside. Remember the chain rule when you do differentiation, yeah? So when you differentiate sine omega t, you get omega cosine omega t. So the math is telling us that not only is the flux linkage changing sinusoidally with time, the induced EMF is also changing sinusoidally with time, but they are not in phase. You should know that there's a quarter cycle phase difference between cosine and sine. So the time instance when flux linkage is at its maximum are not the time instance when induced EMF is at its maximum. It's much clearer if we sketch a graph. So this is the graph for the flux linkage. It's a sine function. This is the graph for the induced EMF, which is a negative cosine function. That's why it has this shape. So do you see that at these two time instants, when we have maximum flux linkages, the rate of change is actually 0. It has a flat gradient. That's why at these two time instances, the induced EMF is 0, instantaneously 0. It's when the flux linkage is 0, they will get maximum induced EMF. That's because the rate of change here is the fastest. The gradient is the steepest when the flux linkage is 0. Oh yeah, many students will ask, why does the flux linkage change direction? That's a good question actually. So remember we have a constant magnetic field that's going rightward. Yeah, rightward. So when a frame is oriented like this, it's entering the frame from this side. Yeah, this side. A coil has two faces, right? This face and this face. So after the coil is rotated 180 degrees, this face will have been rotated to this side instead. So last time the magnetic flux enters the coil through this face, but half a cycle later, the flux enters the coil through the other face. So as far as the coil is concerned, the flux has changed direction. And that's why we have positive and negative flux linkages. Oh yeah, there's another thing that I want to highlight. Now looking at this expression here, if I ask you what can you do to increase the maximum induced EMF, the obvious answers will be, oh, use a bigger coil with a larger area. Oh, use a stronger magnetic field. Oh, increase the number of turns. But do you see this term here? Omega. So if you rotate the coil at a faster speed, the amplitude of this graph will also increase. And it makes sense logically. If you rotate this thing faster and faster, the rate of change of flux linkage also becomes faster. So the induced EMF will also be larger. Alright, that's all. Ta-ta!